Welcome to the first part of the problem-solving session for Chapter 23. Let's begin with the first problem. Here, we are asked to determine the number of electrons which are present in Q equals -1 coulomb of charge. Now, we must remember that because charge is quantized, that -1 coulomb is also equal to minus n times E. In other words, the minus here, because of course we are referring to negative charge, n will tell us how many electrons worth of negative charge, and E, of course, is the constant that tells us what one electron, the charge on one electron. So essentially what we're doing is we're solving for n. Well, the negatives will cancel here, and so because we are solving for the number of electrons, we don't need to have, n itself just represents number of electrons, and it does not matter, the E is just the magnitude of charge. So 1 divided by 1.6 e to the minus 19 coulomb yields a value of n equal to 6.25 e to the 18 electrons. So using the fact that charge is quantized, any quantity of charge Q, which is given to us, we can determine how many, in this case, electrons worth of charge we have, or if this was positive, it would tell us how many protons worth of charge we have. Next slide. Here we are asked, we are given two protons that are fixed to opposite corners of a square. So here's proton 1. We are a little bit out of alignment here in the drawing. And proton 2. And the question is, where should we put the third proton in order for it to experience the greater force? Now this problem requires us to think in terms of the vector nature of force. So let's just suppose for the time being that we were to choose to put a proton at the center of the square. Well, you can see that this proton would feel a force of repulsion due to this proton, and therefore the force would be directed along this direction, the line that joins the two charges, but this proton is also repulsed by this proton, and so feels a force of the same magnitude in the opposite direction. And what we see here is proton divided by r squared, proton divided by the same r squared. The magnitude of the forces are equal, and therefore, since they are opposite in direction, add up to 0. So we certainly wouldn't want to put a proton at the center. Now let's see what happens if we instead put the proton at the corner. Well, of course, this proton is repulsed by this proton and will feel a force that is to try to make it go as far away from the proton as possible, so along the line that joins them away. Now this proton will exert a force that would push this proton in this direction here. Once again, because the sides of the square are equal, the magnitudes of the forces will be the same. When we add these two vector forces, we find that the net force is along the diagonal, or in other words at 45 degrees, of course, because they are of the same magnitude, the two forces exerted, and therefore not equal to 0. And so we can answer the question by saying, yes, let's put a proton on the corner and it will certainly experience the greater force. Next problem. Here in question 3, we're told that there are two protons in a molecule, and these are separated by a distance of 3.8 e to the minus 10 meters. In A, part A, we were asked to determine the electric force that one proton exerts on the other, and in part B, to compare this force with the magnitude of the gravitational force between the two protons. Well, let's go ahead and solve the problem first, and then we'll watch the little video referring to this type of problem. Well, in part A, we want the electric force between the two protons, and of course Coulomb's law says that it will be the constant. We're going to assume the protons are separated by vacuum, and that will be the case for all the problems that we do in this chapter. Proton 1 times proton 2 divided by their distance of separation squared, and of course that was given to us as 3.8 e to the minus 10. But we can simplify this because we know that the charge on proton 1 is the same as the charge on proton 2, so essentially Q1 equals Q2, and so we can just say it equals Q squared divided by R squared. We substitute our numbers, 8.99 e to the 9 for the electric constant, Q, the charge on a proton, 1.6 e to the minus 19 coulombs squared, divided by their distance of separation, 3.8 e to the negative 10 meters squared, and we get a value that is equal to 1.59 e to the minus 9 newtons. In the next part, we're asked to compare the gravitational force with the electric force. Well, whenever we're asked to compare anything, we must quantitatively be able to do so. And so we set out to determine the value of the gravitational force. Here again, because the mass of one proton is the same as the mass of the other proton, we can just simplify this expression by writing G times mass of proton squared divided by distance of separation squared. Well, G, gravitational constant, is 6.67 e to the minus 11. The mass on a proton is 1.67 e to the minus 27 kilograms squared. And we're going to divide that by 3.8 e to the minus 10 meters squared. What do we get? We get a very small number, 1.82 e to the minus 44 newtons. And so now we're prepared to quantitatively compare these. How many times bigger is the electric force than the gravitational force? We take the value of the electric force divided by the value of the gravitational force, and we end up with a number which tells us that the electric force is nearly 35 orders of magnitude greater than the gravitational force. And this is, of course, the reason that we actually can see electrical phenomena. The interaction between the repulsion between two electric charges, or the attraction, as in the case, for example, of a balloon sticking to a wall, defying gravity, etc. Next problem. Question 4 says, consider the following. There are 3 charges located at the corners of a right triangle. Okay, a right triangle means that this is a 45-degree angle, and this is a, this is a 45-degree triangle. And there are 3 charges, Q1, Q3 of the same magnitude, and a Q2 different in magnitude and in fact different in sign. We are told that the separation between the charges A, between Q1, Q2, Q2, Q3 is 0.1 meter. And we're asked to determine the net force on charge Q3 due to the other 2 charges. Now the book started this problem for us because they set up these vector forces. Let's see where they got this. Well, the force between charge 1 and charge 3 is F13. And of course, because we are asked to determine the force on charge 3, we don't care about the force on charge 1, even though they're the same in magnitude. Of course, this one would be in the opposite direction. So we see that the force F13 is directed so that, first of all, there's a 45-degree angle between this force and the horizontal. And if we impose the components of F13, we find that there is a horizontal component, F13x, and of course, F13y. So in other words, F13 is a force, vector force, which has both x and y components. On the other hand, the forces between Q2 and Q3, because Q3 is positive and Q2 is negative, will draw Q3 towards Q2. We call this force F23. And if you notice, F23 is directed along the negative x-axis, and so therefore will only have a component F23 along the x direction, but it will be negative. Well, before we actually get any of the components, let's go ahead and work out the magnitudes of these forces. Let's begin with the magnitude of F13. F13 magnitude equals K times the magnitude of Q1 times the magnitude of Q3 divided by the distance between Q1 and Q3. They're giving us as the square root of 2 times A. Well, the square root of 2 times A is also going to be squared. And so we can simplify this as 2 times A squared, which we will shortly. Notice, however, that Q1 is an absolute value and so is Q3. Now that may be unnecessary in this case since they're both positive, but I'm stressing the point that when we are working with the magnitude of the force, we do not want to consider at all what the sign of the charge is. And this is very important because if either Q1 or Q3 was negative, you would not want to write it as a negative. Well, let's see. 5 microcoulombs for Q1, 5 microcoulombs for Q3, divided by 2 times A is 0.1 meter squared. And this gives us a magnitude of F13 that is equal to 11.2 newtons. Well, next we want to do the same for F23. Again, we focus on magnitude only. Direction, remember, is given by the direction of the component, and because we have drawn our arrows, we can readily see what the sign of each of the components is going to be. Okay, magnitude of Q2 times magnitude of Q3 divided by, this time, A squared, since the distance between them is just A. Substituting our numbers, 8.99 e to the 9 times 2 microcoulombs times 5 microcoulombs. Notice there's no negative sign here. Very, very important that you keep that in mind. Divided by 1 meter squared, that gives us 8.99 newtons. Well, now that we have the magnitudes, we can actually write the vectors themselves. Well, let's begin with F23 since we just ended with it. F23, recall, only had a negative x component. And so here we have the magnitude of that x component. Remember, it lies only along the x-axis. There's no projection on y. So we have, if we want, we can write it this way, 8.99 times the cosine of 180 in the I hat direction with the unit of Newton, but of course you know what that's going to be, minus 8.99 I hat newtons. And if we want to further specify 0 j hat component, since it has none. Now let's go to F13. F13 is equal to 11.2 cosine of 45 I hat plus 11.2 sine of 45 j hat. Oops, keep losing my pencil. Now, of course, cosine and sine of 45 are the same, so these will numerically work out to be the same number, 7.95 in the I hat direction plus 7.95 in the j hat direction. To get the net force on charge 3, we need to add F23 with F13. But adding these means we have to add the x component of F23 with the x component of F13, the y component of F23 with the y component of F13. And for x, therefore, we get minus 1.04 I hat. I'll leave the unit for the end because minus 8.99 plus 7.95 is minus 1.04 plus 0 plus 7.95 gives us 7.95 j hat. Now we'll go ahead and put our unit, and we have effectively solved the problem. Next problem. Question 5 asks the following. It says a proton and an electron are held in place along the x-axis at equal distances to each other and on opposite sides of the origin. Since the electric force is the only one that affects them, when each is released, each will accelerate towards the other. Question: which is going to reach the origin first? Now, asking this question basically says, okay, if this is the same distance as this, the one that's going to reach the origin first is the one that's going to be moving faster. And because they are released from rest, the one that is going to be moving faster will be the one that has the greater acceleration. And of course, that is along the x-axis. Now, this problem asks us to focus on Newton's second law and the fact that the force the electron exerts on the proton is the same as the force that the proton exerts on the electron in magnitude. So the question is, who is going to accelerate at a greater value? Well, in the case of the electron, EL, we have the force between the two, the same for each, divided by the mass of the electron. In the case of the proton, we have the force, same force as the electron experiences, but this time divided by the mass of the proton. Now, if the forces are the same, the only difference in the accelerations can come from the masses. And so because these are inversely proportional, we can say the smaller the mass, the greater the acceleration. And so therefore it will be the electron, which is about nearly 10,000 times lighter than the proton, which will get to the origin first. Next problem, and the last problem in part 1 of the problem solving session. Question 6 says the following. A charge Q, which is positive and equal to 24 microcoulombs, and of course we remember that the micro stands for e to the minus 6, is placed in a uniform electric field which is directed, and by the way, this symbol didn't come out right, perpendicular to the ground. So here's what we know. There is a source charge that created this electric field. It is not our charge. It is an invisible charge. We know the electric field is there, but we don't know and we don't care where the source charge is because we have a mapping of the electric field. The fact that it's uniform means the electric field at every point along the region where this charge is constant. So then it says, consider that not only will the electric force due to this electric field act on the charge, so does the force of gravity. So, being that this charge is subjected to two forces, the question asks us to determine for what mass of this charge will it be able to float in the presence of both fields. Okay, now that's important here because floating implies that there is no net force, and of course this is going to be along the y direction. So equilibrium means our charge is not accelerating, and in fact it's not even moving for that matter. Now let's notice that the gravitational field is directed downward as it always is, and of course the force of gravity on this charge is equal to mg, downward. There is only one way that this charge can have no net force on it, and that is if the electric force has the same magnitude but is opposite in direction, in other words, upward. So here we're going to draw an additional arrow to indicate that the electric field must be upward. This is a positive charge, and positive charges experience electric forces in the same direction as the electric field. Now, the fact that we've said that the magnitude must be equal, but the direction must be opposite, means that when we use Newton's second law, we can look at each of these forces, positive QE because it's directed upward, minus mg because it's directed downward, equals 0. Well, let's see. We are solving for m, so we take mg to the opposite side, m. Now we are going to divide both sides by g equals q times e divided by g. Well, let's see. Do we know the value of q? Yes, we do. It was given to us. Do we know the value of e? Yes, we do. It was given to us. Do we know the value of g? Well, of course we do, since that's all we ever did in Physics 1 was to work with little g as 9.8. So now it's time to enter our numbers so that we can quantitatively be able to say what mass is required of this charge in order for this floating effect to take place. We substitute our numbers and we get a value of m, which is equal to 1.49 e to the minus 23 kilograms. And that tells us that if the charge has this mass, it will float. What if it has a mass which is greater than 1. Oh, I'm sorry, that's not 23, that is just a 3. Oh boy. Okay, so that's 1.49 e to the minus 3 kilograms. So the question is this: what if this is a more massive charge, same quantity of Q, but a greater mass? What would happen to this charge? Well, because the force of gravity would be greater than the electric force, this charge would be experiencing an acceleration downward. If, on the other hand, this charge was less massive than 1.49 e to the minus 3 kilograms, well, the force of gravity would be too small compared to the electric force, and this charge would be accelerating upward. But when it has this value, based on this condition that we established, it will not accelerate whatsoever. Well, this concludes the first part of Chapter 23, the problem-solving session. See you soon.